Question number 2. Let's read the question first and try to understand it. It says determine the resultant internal loadings on the cross section at point D. This is a bit of difficult question. Okay, let me guide you through how to find out those internal forces, because until now we have not studied members subjected to this kind of transverse loads. Now this is called a beam. We learned about axial loads only, and the torsion loads we just started this week or last week. Yes. So in this question, there's no stress related calculations. So what we need to find out, only the internal forces. Some of you may have already learned how to find out internal forces in your statics or engineering mechanics subject before. Okay, right. So let me guide you through how to solve these kind of problems. So if you want to find out the internal forces, first thing that you do, you draw a Freiburg diagram and see if there are unknown reaction forces. If you find unknown reaction forces, you find those reaction forces first using equation of equilibriums. Okay, and then to find the internal forces, definitely we need to cut this open and expose the internal forces. So since we are going to find out internal forces at point D, we are going to cut across D and draw Freiburg diagram for cut portions. Then we will be able to see, again, we are going to do that using the Freiburg diagram. We should be able to write equation of equilibriums and then find the unknown internal forces as well. Right, so we'll start with drawing a Freiburg diagram for the whole system first without cutting it. Okay, so let's write draw a FBD for the whole system. Okay. And before that, some of you might have a confusion about the way the load is applied. Now this is called a distributed load. It is not uniformly distributed, but the pattern of distribution has a kind of a uniformity, right? So do you understand the meaning of this one? This load here, it says at this particular point, the intensity of the load is 4 kilonewton per meter. Right. And then at point B, load is 0. So between A and B, the load intensity vary from 4 to 0 linearly, forming a triangular distribution. So if you want to find out the equivalent total load here as a point load, the area of this triangle provides that answer. Okay, so when you are drawing a Freiburg diagram for this one, first we draw a physical system. So I'm going to draw a physical system like this, the beam. Okay, and next I'm going to draw my external loads, right? Active loads. But here, let me draw the distribution as a dotted line like this, because I'm going to replace this distributed load with the equivalent point load. So once you do that, you find that you can easily find out the external forces, the reaction forces. So what is the equivalent point force? Oh, can you find in place of this distributed load, you are going to introduce now a point load. So that point load should be applied between A and B at one point. Normally, the resultant equivalent force going to go through the centroid of the geometry. Here the geometry is the geometric distribution is a triangular distribution. So I don't know whether you have learned this centroid concept of centroid before. No? Okay. I will introduce you centroid later. Okay. At this moment, just have some idea. It's like, if there's a bigger mass, we don't know exact, or we know the total weight. So how you place the weight of a bigger mass? You put it at the center of gravity, right? As a point load. So similar to that. Okay, so it's like we are going to find out center of gravity of this triangle and then place the load at that center of gravity. But we don't call it center of gravity, we call it centroid. Centroid is a geometric center of the geometry, right? So if you have a triangular distribution, or it's a triangle, a plate, triangular plate like this, then the geometric center is located 1/3 of this height from the base. So if this is the base, this is the base. Okay, from the base, if you measure this length L, and if you take 1/3 somewhere here, so I mark this one as 1/3 of L. So the centroid locate in this line somewhere here. It's like the center of gravity. In fact, if you take the triangular metal plate like this and try to balance it on your finger, you have to keep your finger 1/3 from the base or 2/3 from the tip. Okay, this is the tip. Okay, right. So now this point is actually called the centroid. Centroid is the geometric center. Okay, I will introduce this concept later. Any complicated shape, you should be able to find out the centroid. So you need that understanding when we study bending. Okay, so in week number 5 of 5, I will introduce you centroid. Okay. So at this moment, we'll assume that this is simple geometry, and in this geometry, we mark our centroid, let's say somewhere here, 1/3 from the base. And then if I mark the line like this, so instead of the distributed load, now I can introduce a point load like this. And the size of this point load should be equal to the magnitude of the distributed load. So if I mark this load as P, how to find out the size of this P? The size of this P is equal to the area of the triangle. Area of the triangle. So what is the area of this triangle? So length is equal to 3 plus 1.5. 1.5 is 6 meters. 6 meters. Right? And the base height, this height here is 4 kilonewtons per meter. So this is 4 kilonewtons per meter. This is this height. Okay, so if you multiply this 4 by the distance, you get the applied load, right? So this area of this triangle provides you the total load applied, and equivalent P is equal to the area of this triangle. So how to write the area of a triangle? Half into base into the height, right? So here base is 4 and the height is 6. So this is the total force. So what is the value of that one? Can you quickly do the calculation? 12 kilonewtons. So 12 kilonewtons applied through the centroid is equal to the distributed load, triangular distributed load. right? So that is the external load. Internally, not internally, external reaction force. There are going to be a reaction force at point A and B. They are all vertical because there are no other loads in other directions. So what is the size of that? We don't know, right? So just mark it as A y direction, right? AY and BY. Okay, so and also put the name the diagram. This is A. This point at which we apply the resultant force, we don't know exactly. So just name it as X. Okay. And then here point D and point B. So we need distances as well. We'll mark the distances because later to find the forces, we need the distance. So what's the distance from A to X now? 1/3 of L, right? That is 2 meters. And X to B is 4 meters. Okay. So if you don't know how I got this one, this is 1/3 of 6. Okay. So now can you find out AY and BY? Now you can, right? But in fact, in this question, I think you need only BY. So therefore, find out BY. All right, find the support reaction at B. So what we can do, if I just write force equilibrium in y direction, both AY and BY come to the equation, right? So the easy way is to take the moment around point A, then only BY come for the equation. So you take the moment around point A. Now here, positive direction is anti-clockwise direction. Summation of all the moments should be equal to 0. So can you write the equation now? First, we take the active force P, 12 kilonewtons. 12 into the distance, 2 meters. Okay. Is it in the clockwise direction or anti-clockwise direction? If you apply P only, it is anti-clockwise direction. It is negative. Okay. And then you apply only BY. BY create a anti-clockwise direction moment, that is positive. BY into the distance 6 meters equal to 0. That means now you can find out BY. I did the calculation, I got this 4 kilonewton answer. Right. So now I think we don't need to find out AY, but if you want, you can easily find out AY now, right? Get the vertical direction, Y direction force balance, then you can find out AY. So what our target is to find out internal forces at point D. So we need to cut the member at D and open the internal forces. So I'm going to draw another free body diagram now. This time I'm going to cut the member at D. Like this, and from D to B, I'm going to draw it with a gap so that I have enough space to draw my internal forces. Okay, so this is A to D, and then this is D to B. Okay, now look at the AD portion and add the active and the reactive forces. active force, since I cut through D here, so the height of this force here, I really don't know the value. So maybe X, again, take that as X. So first I just mark my active force as a dotted line like this. Because later I'm going to replace this one with a point load. Same height here, and then it continue up to 0. Now, like before, now we have a like a trapezium, right? Distribution is not triangular, trapezium like. So we are going to mark the force, equivalent force, but it is not at the X now, a different point. Okay, what is the distance here? So it is A to D. Distance is 4.5, right? 4.5 by 1/3. So if you want to really mark the distance, you can mark that distance here. So this point to this point is 1/3 into 4.5. See the distance, right? Is it correct or not? No, it may not be correct because, yeah, I made a mistake here. Why? It is not a triangular distribution. So it's a trapezium. Okay, you need to find out the centroid here. So, but our focus is not this part. Our focus is the other part. So therefore, I'm not going to find out that centroid. Later, I will teach you how to find out the centroid of a different section, I mean the different geometric shape. Okay, now if I just mark the reactive forces at point A, there we have AY. Right. And next, at section D, there should be internal forces. In general, there can be three kinds of internal forces. If there are only axial forces, we know that there should be normal internal force like this. I'll just mark it as N, just to say it is normal. And at the point D, therefore ND. Okay. And there can be a shear force, which is along the cut surface. So I just mark shear force in this direction, or downwards this way, and mark it as V. Normal notation we use for shear force is V. Okay, V T. And next we have, maybe I will use a different color. This one is VT. And next one is the moment in this direction, MT. These are the three possible internal forces. We don't know whether all three are present here, but we can mark all of them. Okay. When I mark these internal forces, I specifically selected the direction. The directions are selected to mark the positive direction. Okay, so you can see MD I mark in anti-clockwise direction. Anti-clockwise direction is positive. VD I mark downwards. Later I will introduce the sign convention. Any shear force that creates a clockwise direction movement is positive. That's why I mark like this. Okay, and normal force always marked against or away from the cross section. Okay, so all these directions I selected purposely, but at this moment you might not understand why. Later we will understand why that sign convention is. So now this part of the freeboard diagram is complete. Then we'll go to the DB side. So DB side also, first we mark our resultant force as a point force here. Let's mark it as P2, this one as P1. So P2 you should be able to find out, and exact location of P2 also you can say now, because we know for a triangular distribution it is 1/3 from the base. Okay, right. Next we have to mark our reactive force By. Okay, so all the external forces are complete, and now we mark the internal forces. So in AD I mark ND out away from the cross section, right? Now in the other part, it should be in opposite direction, so that once you put them together they cancel off, right? So if you don't cut, there are no forces, right? Once you cut, only these forces open up, and then the shear force should mark in vertical direction here, opposite VD, and your moment should be in the opposite direction too. So I just marked like this. This is the moment. Empty, opposite direction. But if you look at how I mark everything, now you can see they are in the opposite directions, right? So that once you put them together, they cancel off. Okay, so now two freeboard diagrams are complete. Our target is to find out ND, MD, and VD. So let's find out what this ND is, and also VD and MD. Okay. So I'm going to concentrate on the free body diagram of DB. So this is my focus now. This free body diagram, okay? This is the FBD of DB. And there, in order to apply equation of equilibrium, I need to know the exact point at which this force is applied. So you may find the distances. The total distance is 1.5 meters, right? 1.5 meters. Therefore, this distance here, let me mark it as A, and this distance as B. So what is A? A is equal to 1/3 of 1.5. Okay. Okay. And also we need the size of the triangle at this base. I'll mark it as X. Also X. Okay. So if I draw a triangle showing that portion like this now, this is X, and the total distance here, this distance is 1.5. Oh, sorry. Yeah, it is 1.5, right? Maybe I don't write anything at the moment. I will draw the whole triangle, and this is 4, and I mark X here and mark these positions. This one is 1.5 and this is 4.5. My proportions are not correct, but you see the point, right? What I did, I just draw the triangular distribution from A to D to B, ADB. So my purpose is to find out X. So what is the value of X? Similar triangles, right? So using similar triangles, you can say that X over 4 is equal to 1.5 over 6. From this, you can find out X. What is the value of X? I got this value as 1 kilonewton per meter. Okay. So with that information, can you write down the value of P2 now? Yeah, is half into the base 1.5 right, is 1.5, right, into the height now is 1. So if you simplify it, you get 0.75 kilonewton. So that is the equivalent load. Okay, so with that information, now you should be able to write the equation of equilibrium for freeboard diagram of BB, considering f d of dB apply equation of equilibrium. Okay, so you are going to write equation of equilibriums for freeboard diagram of dB. Our focus is to find out ND, BD, and MD. So we already know the value of BY. So we found the BY as previously 4 kilonewton, right? 4 kilonewton. This value is 4 kilonewton. Okay, so first to find out ND, we'll write our equation of equilibrium in x direction. Okay, horizontal direction should be equal to 0. So what it says, ND is in opposite direction, therefore negative ND. Any other forces? No other forces in x direction. So this one tells me that ND is in fact is 0. No horizontal force or no normal force. So that we found one internal force now. The second one, we'll find out VT. That means I need to take for equation of equilibrium in y direction. So this one is x direction. Fy should be equal to 0. So we have Vd in that direction, positive, and then By in that direction, and P2 opposite direction, negative P2 equal to 0. So now can you write the values? Vd should be equal to P2. P2 is 0.75. Py negative 4 kilonewton. That is negative 3.25 kilonewton. Okay. So it says that shear force, in fact, in the opposite direction. I mark it vertically up, but it should be opposite direction. And how to find out? Yeah. So there's a comment, right? What is it? Let's ask. Okay. So now can you write the moment balance about D in this direction, summation of all the moments about D MT should be equal to 0. Okay, so what are the forces? There are P2, By, and also MD. So we'll take the P2 first. P2 around D, P2 going to rotate the member around in the clockwise direction, right? If you apply P2, that means it's negative P2 times the distance. That distance is the one that I have calculated as A, right? And then By create anti-clockwise moment around D, therefore it is positive. By times the total distance A plus B is 1.5 meters. Right. Anything else? MD is applied in clockwise direction here, right? I mark it in clockwise direction around D. Therefore, it is negative MT should be equal to 0. That's it. We are not going to multiply moment by the distance, right? Only the force by distance. Force into distance give the moment. And MD is a moment itself. So you don't need to multiply it by any forces, any distances. Okay, now you can simplify this one, right? So P2, we know the value of P2, 0.75 negative 0.75 kilonewton into A we already found as 1.5 over 3 plus By is 4 kilonewton into 1.5 minus MT equals 0. So you simplify this one, you get the answer for MT. Kilonewton meter. Because throughout I use the kilonewton. So if you want, you can substitute in newtons as well. So check whether you can get this answer. Okay, it is a bit complicated, but now you learn how to find out how to replace distributed load with a point load. And once you do that, problem becomes simple. And new knowledge or something new that you have learned is about the internal forces. At a point of hot surface, there can be normal forces, shear forces, or bending moment. Those are the possible 3 forces. So always we mark those 3 if you are not sure exactly what are the internal forces there. But in the axial forces topic, I always mark only the normal force. There's a reason for that. Why? Because we know exactly there won't be any shear forces. There won't be any moments. Okay. The only possibility is a normal force. That's the reason why I mark only the normal forces. Like here, I mark this normal force, right? I didn't mark the shear force here because I know that VD is 0. Okay. And at the same time, I didn't mark this MD here, MD, because I know that it is 0. Okay. Right. Any questions? So now you can try question number 3. With what you have learned just now, you should be able to try question number 3. Let's try. Determine the resultant internal loadings on the cross section at point D. Now you can see that again, we need to cut the member at D and draw a freeboard diagram. Then you can see the internal forces. But before we go up to that level, we need to understand, find out, or draw a freeboard diagram for the system, and then find out unknown reaction forces. Okay, so first let's draw the freeboard diagram for the system, and here we can concentrate on AB link, AB link, right? We don't need to draw BC. BC we can replace with a force or reaction force coming from BC. So let's draw the freeboard diagram. FBD for AB. Okay, so I just draw AB here. This is my A and then B. Okay, and next I will mark my externally applied active forces. Here the active forces are distributed forces. The distribution is a triangular distribution. What is the equivalent force now? The area of this triangle. Okay, right. So the centroid of a triangle is going to be right at the middle. So if you not a triangle, it's a rectangle. Okay, if there's a rectangular cross, the metal piece, yeah, the centroid is at the center. How to find out the centroid? You just mark the two diagonals. The intersection point is the centroid. See, centroid. So therefore, your force now should pass through equivalent force. Resultant force should pass through the centroid. So this is the resultant force P. So what is the value of P? It is the area of the cross section. Sorry, the rectangular distribution is 1.25. The side is 1.25, right? The side here 1.25. The total length 1.5. So the total force here is 1.25 into 1.5. So this is the total force in kilonewton. Okay, so then you mark the reactions, reactive forces. At point A, there should be a reaction. At point B, there's a reaction. At point A, how you mark your reaction force? From your previous knowledge, can you mark reaction force at A? What kind of joint it is? It's a pin joint, right? It can rotate about a point. So at a pin joint, we don't know exactly which direction the force is. So then we mark X and Y components. So it is, we'll mark the X and Y component here. This way, my Y, AY, this way my AX. Actual force actually, like this, R. Oh, I shouldn't draw that one, otherwise you get confused, because it should be this way, right? This is the R. Don't draw it, okay? So anyway, AX and AY. And how about the point B? It's also kind of a pin joint, but from the way it is attached to a link BC, we know that exactly the reaction force going to go through that one, right? It's like a rope. right? Hanging from a rope. So therefore, reaction force here going to apply along BC will mark that force as FBC, right? And it creates an angle. The horizontal surface, we mark it as theta. Theta is the angle. Anything else? That's it, right? Let's mark the distances as well. So later we need these distances. This is 0.75 meters. This is also 0.75 meters because centroid is at the center. Okay. Now to find out the internal force at D, we need the reaction forces first. So we'll find the reaction forces using this Freebird diagram. Find support reactions using FBD. So that means we need to find out AX, AY, and FBC. Okay. So by observation, I can say that if I take the moment around A, you can immediately find out FBC. Right. So we'll find FBC first. Take the moment around A. Summation of all the moment about A should be equal to 0. Can you write that one? First, we'll take the FBC, apply only the FBC. So FBC has a horizontal component and vertical component. We take the vertical component. So vertical component of the FBC is FBC into sine theta or cosine theta. Sine theta, right? This is the force, vertical component. And the distance to that point from A is 1.5. Okay. Is it a positive moment or negative moment? Around A. It's a positive moment, right? Therefore, it is positive. Okay. Then take P. P going to create clockwise moment. So therefore, it is negative. So P times the distance is 0.75. Any other forces? No others, right? Therefore, this is equal to 0. Now, only unknown, there are two unknowns, sine theta. Do you know how to find out sine theta? Angle theta? By analyzing the triangle geometry, you should be able to find out theta. So if I draw this triangle, B, C, and I mark it as F. Okay, and their CF is given as 2 meters. BF is given as 1.5 meters. So now can you find out BC? Or else you can multiply this one by 2, 4. This is multiplied by 2, 3. Therefore, this becomes 5. Pythagoras theorem. Okay, is the angle theta. Therefore, now I can write sine theta is equal to 455. Correct? Understand? Yeah. Or else you simply find out BZ using Pythagoras theorem, right? And then it is going to be 2 over BC. Okay. Now I can write this way: FBC into 4 by 5, this is the sine theta, into 1.5 minus P is 1.25 into 1.5 into 0.75 equal to 0. Okay, this will tell you the value of FBC. I got this answer 1.1719 kilonewton. Here's FBC. So now find out AY and AX, because we might need them. So I take force in Y direction. That is AY minus P plus again FBC into sine theta. So can you do the calculation? I write the answer I got. 0.9375 kilonewton. This is the answer I got. Okay, to find out AX, you write your force balance in X direction. Negative AX. Now I assume that you can do this one by yourself, okay? Negative AX, AY and P will not come in this equation. And FBZ is horizontal component, right? That is in the positive direction, therefore it is FBC times cosine theta. So what is the cosine theta here? From the same triangle, I can write cosine theta is 3/5. So that means after simplifying, you should be able to find out AX. I got this answer 0.7031 kilonewton. So I know the unknown reaction forces, all the unknown reaction forces now. Right. So once you complete this one, next, my question is, I need to find out the resultant internal loadings on the cross section at point T. So that means I need to cut this member at D here and draw a freeboard diagram for the cut portion. So here I'm going to draw the freeboard diagram only for AD, right? We don't need the DB. Previously I draw that one just to show you the whole picture, right? So just right here, draw a FBD for AD, only AD. So now can you do it by yourself? Draw it by yourself. Point A, here is point D. First mark the active forces. So mark the distribution of the force as a dotted line, and then mark the resultant point load. So here we mark it as P1. you should be able to write the value of P1. The value of P1. P1 should be equal to, again, the area of the rectangle. Now its base is 0.5, right? So it is going to be 1.25 times 0.5, 0.5 kilonewton. So this is the P1. And then you mark your reaction forces, support reactions, AY and AX. So we already know the value of AX, AY. Okay. And next, you are going to mark your internal forces at section D. Can you mark the internal forces? Mark all three possible internal forces. Okay. The first one is the normal internal force. And the second one is the shear force, which is applied along the cross section. Mark it downwards, VD. And the last one is the moment, MD. So our target is to find out these three, ND, VD, and MD. So can you find out ND first? To find the ND, you write your equation of equilibrium in x direction. If x equals 0, that means ND minus AX, anything else? Nothing, right? Equal to 0. So from this one, you can find out ND. Okay. So the answer in your handout, can you find the answer? Given? Oh, okay, I will write the answer then. So the answer is 0.703 kilonewton. And then to find out VD, we take the force balance in y direction. Now this part I will leave for you. Complete this one and see whether you can get this answer. Zero 0.3125 kilonewton. Okay, so if I've got that one, now write the moment balance at point D. Summation of all the moments around D should be equal to 0. Now write it by yourself. Okay, so I hope that you know how to write the equation. This is the answer. 0. Again 3125 kilonewton meter. Have you got the same answer? Let me double check. Yeah, I'm correct. So the question is it just me, no sound, or have sound again? Because I didn't talk, I let you write. Can you hear me now? Yeah, thank you. Right, any questions so far? So the last two questions may be new for you, but I know that some of you have already learned these things in your higher diploma or your associate degree mechanics of or engineering mechanics subject. Right. So if you don't have any questions, let's try question number 4 as well. And after that, we'll have a short break. Okay, so shall we read it together first and try to understand the question? So it says a load P is applied to a steel rod supported as shown by an aluminum plate into which a 12 mm diameter hole has been drilled. You understand which one is aluminum, which one is steel here? It says there's a steel rod, right? Load P is applied to the steel rod. So that means the blue part here is the steel. This one is made of steel. And the bottom part here is aluminium. Okay. And there's a hole in the aluminium plate. That hole size is 12 millimeters given in here. 12 mm hole. And into that, they have put a steel. It's like a bolt with a head. I hope that you can visualize what it is, right? So it's a bolt like this with a pin like this. And through the hole in the plate, it has been put in. Okay, and then the load P is applied. Knowing that the shearing stress must not exceed 180 megapascal in steel rod and 70 megapascal in the aluminium plate. So that means the shear stress maximum for steel should be less than or equal to 180 megapascal. Or you can write tau S max is equal to 180 megapascal. And for aluminium, tau aluminium maximum should be 70 megapascal. Determine the largest load P that can be applied to the rod. So we need to find out P. Actually, we need to find out P max. What is the maximum of P? Okay, this is what we need to find. So let's see how it is this whole system can fail. Right? We really don't know whether steel going to fail or aluminum plate going to fail here. Okay, so we'll take both possibilities and see, do some calculation and see which one going to fail first. Okay, so if the steel going to fail, how it is going to fail and which way it is going to fail. So I'm going to pull it downwards P and assume that aluminum plate is perfectly rigid, it is not going to fail. Okay, and then once you pull it downwards P, the steel plate going to shear off along this way, right? It's like a circular section going to shear off. So if I draw that part which is going to shear off, it should be like this. Okay, and it is going to shear off in all around like a cylinder. You can visualize that one, right? Yeah. So what is the cross section of this one, or the diameter? This diameter. What's the value of this diameter? 12. And the thickness? 10 millimeters. Yeah. So if I want to find out the shear area, and if I mark it as AS, because later we know that shear force or shear stress tau is equal to shear force P, whatever the force that applied, divided by the cross-sectional area. So what is AS? Let's mark this one as T and this one as T1, or this one T1. So AS is equal to pi T1, that's the perimeter, into the height, right, or thickness, T1. So this is the area. Okay. Therefore, we can say that assuming failure of steel part, steel, say steel part, I say steel part, shear area AS is equal to pi T1 into T1, that is pi into D1 is 0.012, T1 0.01. We can do the calculation. I got this answer. In fact, you don't need to simplify here. Okay. We can see that steel pin fails when tau is equal to tau max, right? So it is equal to, let's say, P max, when the force P is equal to P max, and it divided by AS. So this one tells me that I can find out the P max when the failure happens using A multiplying AS by tau max. That is 376 into 99 by minus 6 into tau max for steel, right? Maybe I mark it as S max. Okay, S max. That is given as 180 megapascal. So the answer is 67.858 into 10 power 3 Newton. So this is the P max. But this is assuming that's still going to fail, right? So let's take it as number 1. Next, we'll assume that aluminum plate going to fail and steel is perfectly rigid. Okay. Assume aluminum plate will fail. So then how is going to fail? When you pull down, where the aluminum plate going to fail? Can you mark the cross section and draw a cross section of the failed part? It is going to fail through these points, right? This section. You pull it down, then it is going to shear off there. So it's like again a disc with a hole in the middle like this, and the shear area is the cylindrical area here, this area, all around cylindrical area. And here again you can mark the diameters, the total diameter here. What is the size? 40 millimeters. D2 is equal to 40 millimeters, right? And the thickness T2, what is it? 8 millimeters. Okay. Now you can write the shear area here. A is equal to pi T2 into T2. That is pi into 0.04 into 0.008. So you do the simplification, I found this answer 1.00531 into 10 to the power minus 3 meters squared. That is the shear area now. Okay, now we consider aluminum plate fail, right? So aluminum plate fails when tau aluminum maximum is equal to P maximum over AS. Now this is the aluminum plate area. So now we have another value for P maximum, assuming failure of aluminum into AS. 70 megapascal into 1.00531 into 10 to the minus 3. I did the simplification, I got this answer. So this is the second value for Pmax. So if you apply this much, aluminum going to fail. And if we apply 67 something, still going to fail. Now you have the answer, right? So therefore, what is the maximum P that can be applied? P max. What is the answer? Yeah, 67.858, right? Because that is the maximum it can withstand. If we exceed that limit, still going to fail. But we know that aluminum is softer, weaker than steel. Why here aluminum didn't fail, but steel failed? What is the reason? Cross-sectional area, right? You understand the practical side. Okay. So it's not only about the numbers, okay? You have to think about the practical side. Right. So answer is 67.85. Okay. Right. So let's have a short break. We'll start at 8:45. Okay. So meanwhile, if you have any questions, you can ask those questions from me. let's continue. Question number 5 is a easy question. Okay, I'm going to leave it for you. And if you have any difficulty, let me know. I can guide you through later. Okay, so let's go to question number 6. This is also quite easy, but again, just to show you right steps, maybe I'll do this one quickly. Okay, so we'll read the question first. It says, determine the displacement delta CA of the composite bar under the loading as shown. So this is a composite bar. So what do you mean by this delta CA here? Do you understand it? It is the displacement or deformation. I use displacement of C with respect to A. So how far C has moved with respect to A. So that is what that notation means. Okay. NA is fixed. Cross-sectional areas of AB section and BC are given, and also EAB and EBC are given. That means they are made of 2 different materials. So we quickly write what is given. AB given as 500 millimeters squared, and A of BC 200 millimeters squared, and E, Young's modulus of AB 100 gigapascal. So that means 100 into 10 to the power 9 Pascal. Right? EBC 200 gigapascal. So those are the given information. What to find? We know that we need to find delta CA. What is this value? Now, the applied load is an axial load. So deformation is in the axial direction, and it is a composite member. We know if it is a normal one without, a same diameter, same material, only one axial load, internal load is the same, then we know how to find out delta, right? Any questions? If not, can you switch off your microphone, please? Somebody is okay. Delta is equal to PL over AE. Aha. Mr. Lo Chun Nok, could you switch off your microphone, please? Okay. Did you hear me? You can't hear me, right? Okay. So the deformation delta is given as PL over AE. But we cannot use this equation to find out delta CA, right? Why? It is applied only for a section where cross section is the same material, and also internal force is the same. And also you can remember, again, I'm going to write this P here also, internal force. Okay, so we are going to use this equation to find out this delta CA. So we'll do the calculation. So therefore, the total axial deformation is what we are going to find out at C, delta CA. So this delta C with respect to A is equal to delta C with respect to B plus delta B with respect to A. Right. So this is coming from the principle of superposition. And we can write this delta C with respect to B, that is from B to C, everything is constant. Therefore, I can apply PL over AE equation. It's going to be P BC into L BC over A BC E BC plus from A to B, it is P AB into L AB divided by AAB into EAB. So now PBC and PAB are the internal forces, right? So if you want to find out those things, you have to cut the member from BC between BC, O, and AB. But here, now with experience by observation, you can say that PBC is equal to PAB is equal to the external force, right? Because there's only one force. So you can write by observation. But you can't use this observation all the time, okay? Only if there's only one force. Forces PBC should be equal to PAB and should be equal to 60 kilonewton. The rest is known, so therefore now you can find out delta CA. PBC 60 to the power 3. LBC is given as 300, that is 0.3. ABC 200 millimeters squared, right? That is 10 power minus 6 meters squared. And EBC 200 gigapascal. And then PAB again 60. LAB 400.4. AAB 500. EAB 100 gigapascal. Okay, so you can simplify and get this answer, see whether you can get the same answer like me. Okay, so it's not that difficult. Only thing you need to understand, you cannot use that equation for the compound member, right? But we can identify the sections where you can apply the same equation, that equation for the deformation, and then add them together to get the total deformation. Right. Next, let's go to question number 7. Question number 7 is based on, we have to use the Poisson's effect. Okay. So let's read the question first. For a 10-meter rod, the L is 10 meters, right? 10 meters. Made of the material with Poisson's ratio nu equals 0.3. That has elongated by 12 millimeters. So it's an axial elongation. So this is the delta. So if I mark this direction as x, so this is delta x. What is its new radius if originally it had a radius of 50 millimeter? So this is the original radius. Let me mark it as RO, original radius, 50 millimeters. So can you understand what is going on here? So originally, the cross-sectional area is 50 millimeters. The radius is 50 millimeters. So let me draw a kind of an exaggerated diagram here. This is the original cross-section. Okay. And then after elongation, it is going to be smaller, right? Am I right? Why this becomes smaller? Because axial elongation always accompany with the lateral direction contraction. So as you extend, stretch, they are going to be lateral direction contraction. So diameter going to be reduced. So let me mark the original diameter here, original radius, because it is related to the radius, right? This is the original radius, RO, 50 millimeters. And let's say that after the deformation, it becomes smaller. Now this is RF. So this is what we need to find out. So this distance here is the reduction in the radius. We'll mark it as delta R, reduction in the radius. Okay. Or maybe I'll mark it differently so that you understand it better. Millimeters. Maybe I will mark it vertically here. So this is RF, final radius. And this distance here is the reduction in the radius, delta R. So I'll mark the vertical direction, this direction, as Y. Okay. So this is because of the strain in the Y direction. So X direction, there's a strain, and now X direction strain is accompanied with the Y direction strain. So the relationship between those two strains are given by the Poisson's ratio. So equal to Poisson's ratio, we know that nu is equal to negative epsilon y over epsilon x. Okay, so this is axially long strain, and this one is lateral strain. So Poisson's ratio provides you the ratio between those two as a negative value. So the strain Poisson's ratio is given as 0.3. We should be able to find out epsilon x because we know the delta x and also original length. So if we find this epsilon y, then we should be able to find out the contraction. Right. Okay, so let's start. We have to find RF. This is the value that we are going to find out. Let's do the calculation. First, we need to find out axial strain, right? Find the axial strain epsilon x. Epsilon x is equal to elongation in that direction divided by original length LO. Your delta x is given as 12 millimeters into 10 to the power minus 3 to convert it to meters, because length is given as 10 meters. So we can find out the strain now, 1.2 into 10 to the power minus 3. So this is the answer I got. Okay, now let's use the definition for Poisson's ratio, this one, to find out epsilon y. Therefore, lateral strain epsilon y. We'll find that one from the Poisson's ratio. Nu is equal to negative epsilon y over epsilon x. That means epsilon y is equal to negative v times epsilon x. Nu is given as 0.3, and just now we find out epsilon x as 1.2 into 10 to the power minus 3. Okay, so if you simplify this one, you get this answer, negative 3.6 into 10 to the power minus 4. So this is the epsilon y. So now if you visualize what is going to happen to this lateral direction radius, now you can write an equation for epsilon y. Okay, so initially we had a radius of RO, and after, because of the lateral contraction, now it become RF. So this reduction in radius in that direction is the delta r, small r. So now we can write, therefore epsilon y is in fact can be expressed as delta r over RO. Okay, so here now we just found the epsilon y, and RO is a known value, means we can find out delta r. This implies delta r is equal to epsilon y into RO, that is negative 3.6 into 10 to the power minus 4 into RO. RO is 50 millimeters. I multiplied in millimeters, therefore my answer should be in millimeters, because epsilon has no units. I got this answer, negative 0.018 millimeters. So our question is, we need to find out RF, right? Therefore, new radius after elongation is RF. This should be equal to RO minus delta R. It's 50 minus 0.018, 49.982 millimeters. Okay, so since this is a circular cross section, all around same reduction. But if it is another shape, you need to consider Z, X, Y, Z, all directions contractions. Any questions? Okay, if not, I'm going to go to the next question. That is the last one, question number 8. By looking at the diagram given, I know that it's a statically indeterminate problem because there are two supports. We don't need two supports to keep this structural member in equilibrium. You can remove one, right? So that means one support is a redundant support. In this kind of arrangement, using equation of equilibriums, you can't solve this problem. We need additional equation. So in the class, I explained to you, we can write another equation using principle of superposition, additional equation. Okay, so that is the approach that we have to use for this equation. So it says, for the uniform solid shaft, determine the support reactions at fixed supports A and C. So here what we do, first we are going to remove one of the supports and then replace it with a reaction force. We get a free body diagram for the system by replacing one of the supports. So let's draw that free body diagram first. I'm going to draw the free body diagram of this member ABC. So A is fixed. I'm going to keep A only. This is A. Still it is in equilibrium. Why? We don't need support C. So in place of support C, I'm going to replace it with a reaction force RC. Okay. Let's mark the externally applied forces as well. So here 8 kilonewton, 8 kilonewton. Okay. And the total elongation of this system is restricted actually. Even though we apply the force, it is not going to elongate. Okay, so that means here, if you want to find out total elongation delta T, total should be equal to 0, right? Because A and C are fixed supports. And now we can replace this system with two systems. In fact, I can apply only the loads first and let it freely expand, remove the reaction RC. And then I can find out the deformation, axial deformation. And also I can apply only the force R, the reaction force only, RC, and find out the axial deformation again. So let me draw the equivalent system I just draw only the loads this time. Eight kilonewton. So as a result of this applied load, this system going to expand now because no reaction force. Let's take that expansion or elongation as delta L, meaning that it is due to load delta L. This is point A, this is point C originally, right? This is C. And to get the total effect, I need to introduce the reaction force as well. So let me draw the reaction force only now. Okay. So once we apply the reaction force, this member going to contract, right? Because it's a compressive force. This is the RC, contract. The amount of contraction, let's mark as delta R. I'm going to change this arrow here to show the direction of expansion. And one is delta L is expansion, delta R is a contraction. Okay. Now the total effect, using principle of superposition, it says that once you add the two effects, delta L and delta R, it should be equal to delta T. Okay. So you can say from principle of superposition, delta T should be equal to delta L plus delta R, and this should be equal to 0. And this will give me one important equation to solve this problem. So if I want to find out delta L and delta R, what you have to use? You can use the equation for elongation, PL over AE. I can use this equation. So let me just mark this one as case A, this one as case B. Okay. Now, shall we find out delta L? So I'm going to find out this delta L and delta R. Right. For case A, estimate delta L due to loads only, because we apply only loads there, right? So what is the total contraction delta L? Can we directly write delta is equal to PL over AE? Now here there are two parts, right? So if I mark this A to B as part 1 and B to C part 2, so we have to apply delta equals PL over AE equation to BC and AB separately and add them together. Okay, because it's a compound member. You can say delta L is equal to delta AB plus delta BC for the compound member AC. So that means delta AB means PAB into LAB over AAB and EAB. Now here area and the same material, right? Therefore, A and E are the same. So I just keep AE. Okay. Plus delta BC is PBC times LBC over AE. Okay, so now PAB and PBC are internal forces, right? We need to find out those two values. What is PBC? If you want to find out PBC, you need to cut the member between B and C. Let's say I cut somewhere here. Okay. And then take the right side portion and draw a freebird diagram. Then you can find out whether what is the internal force PBC. So I just draw that part. This is C and this one is X. So therefore X. And this is the PBC here. PBC. So are there any external loads on BC? No, right? So this one directly tell me that PBC is equal to 0. So that means this part is actually 0. So there's no elongation for the BC part. PAB, if you want to find out PAB, you need to cut it between A and B, then draw a freebird diagram. This is B, this is C, and this is Y. So this is the PAB. Okay. And the external forces 8 kilonewton each. Right? So now you can find out PAB. So by observation, you can write what it is, right? So PAB equal to 16 kilonewton. So now you can simply substitute the numbers and find out delta L. That is 16 into 10 to the power 3 into LAB. LAB is 2 meters. AE, those values are not given, right? Just keep it as it is, AE. Okay, and we got another equation here and mark that the equation as A. And next we need to find out delta R. For that we need to analyze case B. For case B, estimate delta R due to support reaction. At C. So now when you look at case B, how many portions, different portions are there? Is it a compound member or just a single member? Single member, right? So only one member. So you don't need to write two equations here now. It is delta R is equal to PAC. PAC now, right? PAC into LAC divided by AE. Same A, same E. So what is AC? RC, right, is very obvious. So now it is RC. LAC, 3 meters, correct? 3 meters divided by AE. So we got the another equation B. Now, do you understand why they are the L? We have to use LAZ, right? Because we applied for the whole member. Okay. So now from equation number 1, right, we can substitute the values of A and B in 1. A and B in 1. So that one tells that delta T is equal to delta L plus delta R, that is, and it is equal to 0, right? That means 16 into n power 3 into 2 over AE is equal to, sorry, plus RC into 3 over AE is equal to 0. And here AE cancels off. So now you can find out RC. I got this answer, 10.67 kilonewton. 10.67 kilonewton. Is it a compressive force or tensile force? RC. I got a positive answer, right? That means the marked direction is correct. It's a compressive force. Okay, compressive. Now we need to find out the reaction in the support A. This is the first part, one of the answers, reaction at C. So if you want to find out the reaction at A, we need to draw a free body diagram for the whole system again. To find reaction force at A, FBD for the whole system. So if you look at the whole system, yeah, now I'm going to replace A with the reaction force there. Okay. Eight kilonewton, and then here I know RC in this direction. RA, I don't know the direction, I just mark this way, RA. Okay. So this is A, B, C. So now it's a matter of applying equation of equilibrium, right? For equilibrium, I can write, if I take the force balance in x direction, all the forces add together should be equal to 0. Yeah, here to make our life easier, let me now take the force balance in this direction. Okay, that is also okay. Huh? Okay, so that means RA -8 plus RC is equal to 0, right? That means RA is equal to 16 plus, also negative, right? Negative RC. RC is 10.67 kilonewton. So you get the answer, 5.67 G3 kilonewton. Okay. Is it a positive answer, negative? Positive answer, right? That means the direction I mark again correct. So what kind of force it is? Tensile force or compressive force? It's a tensile force, right? We are pulling tensile force. So its reaction is tensile. All right. So that's it, right? So I think today we have covered all the key sections that we have learned under axial forces. And they are the major objective in that topic is for us to learn how to use equation of equilibriums. So today we have applied equation of equilibrium many times. Now I expect you to do it without my help anymore, right? You can do it now, because without this experience, when it comes to the bending topic, you are going to be in big trouble. Okay, so learn it. Those who are online, if you miss anything, right, about the equation of equilibrium, how to write them, learn it. Okay, so we have now practiced several times. Next thing is we apply, or we use the Hooke's law, and from the Hooke's law we learn how to write the equation for elongation, delta equals PL over AE. So we use that equation today. And also we learn about Poisson's effect, right? So today we did a question on Poisson's effect. And lastly, we learned about statically indeterminate problems. And now the last question also based on that. So we revise everything that we have done before. Okay, right. So I hope that you have done your assignment, but I saw that some of you have not submitted yet. I think those who have not submitted may not be online too. Okay, so they are in troubles. Right. I think I'm going to stop here today, but if you have any questions that you want to discuss with me, you can talk to me, and let's meet this Friday again. There I will complete the torsion topic, and I'll give you the second assignment. It is based on torsion. Okay. For this subject, you need to do a lot of exercises, practice yourself. Otherwise, you will be in difficult situation when it comes to solving problems by yourself. Okay, right. Let me think about any announcements. Yeah, so I need to remind you again about the WIE. Those who have not any opportunity for WIE, now it is time for you to look for those opportunities. And these days, we are organizing some online talks, career talks, that is targeting for your senior year students. But if you wish to join those career talks, please join. You are receiving emails, right? No? Okay, then they are directly going to your seniors only, right? But if you are interested, I can just post the link because they are online presentations. Then you can join in. You have to register only, just register and then take part in those things. You can ask some questions like, can I have WI opportunity or the internship opportunity, right? They are very happy because they want the graduates from us. They are looking for students, the graduates to give them employment. That is number one. Next thing is get ready with a good CV. If you don't have a good CV, there's a service for CV X-ray service. I hope that you already received some emails, right? Use that service and have a good CV for you. That is going to be useful for you. Yeah, that's it. See you next week. Oh, this Friday. So I'll be online for a few more minutes. So if anybody online, if you have any questions, you can ask those questions.